Welcome. In this video, we will cover Chapter 10, Radical Reactions. Free radicals form when bonds are broken in a homolytic fashion. This means that the two electrons that comprise the bond are split evenly between the two atoms attached in the bond. It forms two new species, each with one electron. This can often occur with heat or light conditions. The single barbed arrow of the fishhook represents one electron moving at a time. Most of the chemistry we've looked at to this point is two-electron chemistry. We use two barbed arrows to show the movement of two electrons. To show the movement of one electron, we use a single barbed arrow. A carbocation contains an sp2 hybridized carbon with an empty p orbital, while a carbanion contains an sp3 orbital that is filled with the two electrons. Radicals contain a hybrid of these two conformations, either sp2 or a shallow sp3 that rapidly interconverts. The stability of free radicals mimics the stability of carbocations. A tertiary radical is going to be more stable than a secondary, which is more stable than a primary. These species are neutral, but have an incomplete octet. The bond strength of a carbon-hydrogen bond is inversely proportionate to the carbon radical stability that can be formed. The more stable the resulting radical, the weaker the bond and the easier it is to cleave. Radicals are also stabilized by resonance. This is similar to carbocations. If we're able to stabilize a radical by delocalizing the extra electron over multiple atoms, then this will be a more stable radical. For example, the allylic position is able to interconvert between having in the radical on this carbon and this carbon. The more resonance forms that can exist for a specific radical, the more stable that radical will be. This follows a similar trend to carbocations, where a resonance-stabilized radical will be more stable than a tertiary radical. The stability of a vinylic radical also mimics a vinylic cation. The carbon-hydrogen bond of an sp2 carbon at a double bond has a higher bond dissociation energy and forms a less stable radical. Next, we will look at some of the patterns in the radical mechanisms. These are the different ways that electrons can move around with regards to radicals. Similar to carbocations, we will have some distinct patterns, but the patterns will be different than the patterns we learned for carbocations. The patterns are as follows: homolytic bond cleavage, addition to a pi bond, hydrogen abstraction, halogen abstraction, elimination, and coupling. Over the next few slides, we'll go through each of these patterns. One of the interesting aspects of these patterns is that each pattern has a forward and backward process. So we can really group our 6 patterns into 3 processes: the homolytic bond cleavage, addition to a pi bond, and hydrogen abstraction. The radical mechanism can also be divided into 3 stages. The initiation, where the radical is formed. This stage has a non-radical species become 2 radical species, and the termination and propagation steps. The propagation step starts with the radical and ends with the radical. During the propagation, no radicals are destroyed overall. And then finally, the termination step, where we take a radical species and form a non-radical species. This often occurs when 2 radicals bond together to form a new sigma bond. Let's look at our first radical reaction. This is the chlorination of a hydrocarbon. If we take methane and release it to chlorine gas with a light catalyst, then we can produce methyl chloride and HCl as a byproduct. The first step of this mechanism is that a radical is formed in the initiation stage. The chlorine-chlorine sigma bond is homolytically cleaved to form two chlorine radicals. Once these radicals are formed, the initiation has been completed. The next step is the propagation stage. Propagation stage always starts with the radical and ends with the radical. Here, our radical species employs hydrogen abstraction to form a radical on the methyl group. This carbon radical can then create a new bond with chlorine doing a halogen extraction. Now we've created a new carbon-chlorine bond. The final stage will be a termination stage. This is where two radicals combine to form a non-radical species. This can happen in several different ways. An example could be two chlorine atoms coupling together, a methyl radical and a chlorine radical combining together, and two methyl radicals combining together in coupling processes. The sum of the propagation steps can give the net reaction. In this case, one molecule of methane can combine with one molecule of chlorine to form methyl chloride and hydrochloric acid. During the propagation step, a chain reaction is occurring. The products for the later steps will serve as the reactants for the earlier steps in the mechanisms. One limitation of this reaction is that since it's a chain reaction, polychlorination can occur. For example, one molecule of chlorine can create methyl chloride, and then a second molecule of chlorine can create methylene chloride. A third molecule of chlorine can create chloroform, and a fourth molecule of chlorine can create carbon tetrachloride. In order to obtain just methyl chloride, we will need excess methane relative to the chlorine, and this will allow the monochlorination to be the major product. In order to start the initiation stage of a radical reaction, often a radical initiator is used. These possess a weak bond that can homolytically cleave in the presence of heat or light. Common radical initiators are dihalides, alkyl peroxides, and acyl peroxides. Radical inhibitors are used to prevent chain reaction processes from initiating or propagating. Some of these are stabilizing agents and compounds that can be easily formed to stabilize radicals. For example, hydroquinone will react with two radicals and quench them. Halogen reaction can occur with both bromination and chlorination. Bromination is much slower than chlorination because it has a higher activation barrier, and that means bromination is much more selective than chlorination. Let's say we have a substrate of propane. This substrate has two different types of atoms that could be halogenated. We could halogenate on the two hydrogen atoms of the methylene, and we can halogenate on the 6 hydrogen atoms of the two methyl groups. Chlorine will react with both sets of protons indiscriminately and form two different major products. Since the secondary radicals are more stable than the primary radicals, the secondary halide will be the major product. The hydrogen abstraction and the activation energy needed to form the secondary radical is much faster and much lower than a primary carbon. Now, if we subject the same propane to bromine, we see a 97:3 ratio of the two products. This is because bromination will be much more regioselective than chlorination since it's a slower reaction. If we want to obtain a larger percentage of the more substituted halogen, we should use bromine instead of chlorine. We can then compare this to bromination at a tertiary position relative to a primary position. Chlorinating at a tertiary position will give us a roughly 2:1 ratio of products. However, bromination at the tertiary position will produce nearly 100% of the bromination at the more substituted position. If we wanted to obtain some of the product at the less substituted position, we will want to use chlorination. And even after this, we will still have to isolate the minor product to obtain the material. If halogenation at the position in question will form a new chiral center, then the product will be formed as a mixture of stereoisomers. This means that the halogenation of butane will form three different products. It'll form a racemic mixture of the chlorination at the secondary position and the chlorination at the primary position. If the starting material contains a chiral center, for example S3-methylhexane, halogenation at this position will produce a racemic mixture. The stereocenter will be destroyed once the radical is produced at this center. If we compare the bond association energies of several different types of carbons, we see that the allylic hydrogen has the lowest bond association energy and will be the most reactive, while the vinylic will be the least reactive. Bromination of an alkene will be selective for the allylic carbon. But one limitation of this reaction is that the bromine can also do addition to the alkene in a competing reaction. If we want to brominate at the allylic position, we need a specialized reagent that can perform this reaction. This reagent is called N-bromosuccinimide. It is able to donate a bromine radical, but is not able to do an addition reaction. This reaction begins with a initiation step to form the bromine radical. Then propagation will produce an allylic radical, which can then be combined with a molecule of bromine to form the new bromoalkane. Antioxidants are a series of compounds which can react with radical species. These are radical inhibitors. They will often contain a phenol structure or a polyphenol structure which is a hydroxyl group attached to a benzene ring. The hydroxyl group is able to trap a radical. For example, BHT can undergo hydrogen abstraction to scavenge the radical that could otherwise initiate an auto-oxidation chain reaction. There are many natural antioxidants which nature uses to remove the free radicals in biological systems. Vitamin E is an example of a hydrophobic free radical scavenger, while vitamin C is an example of a polar free radical scavenger that can make its way into the blood. Recall, in Chapter 9, we learned hydrohalogenation in the presence of a peroxide will lead to the anti-Markovnikov addition pattern. This is because the peroxides initiate a radical mechanism of action. The beginning of the reaction starts by the thermal homolysis of the peroxide, which initiates the formation of a bromine radical and HBr. During the propagation step, the bromine radical can then react with the alkene. It can generate either a tertiary radical or a secondary radical. In this case, it's going to form the tertiary radical because that radical is more stable and favored. The bromine radical adds to the pi bond, giving the more stable carbon radical. That carbon radical can then engage in hydrogen abstraction to form the product. The final step of this reaction will be a termination step, which can destroy two bromine radicals. Because of the propagation step being a chain reaction, free radical conditions are often used to form polymers. Polymerization process joins together many small units of monomers into a long chain. For example, ethylene can be polymerized into polyethylene. This reaction undergoes a similar process, radical chain mechanism. First, homolytic cleavage occurs, which creates two alkoxy radicals. One of these radicals can then do an addition to a double bond, which forms a new radical, which can propagate to additional alkenes. Every alkene that's added continues the length of the polymer. The summation of the propagation steps gives the overall net reaction. And then finally, the reaction is terminated with an additional radical-radical coupling. Different polymers of different monomers will have structures that result in different properties. These properties can be used for different applications. For example, the polymer of propylene can be used for carpet fibers and car tires. Styrene can be used for television, radios, and styrofoam. Vinyl chloride is used for PVC piping in plumbings, CDs, garden hoses, and raincoats. And then finally, tetrafluoroethylene can be used to make the non-stick coating for frying pans called Teflon. The radical process is also used in the cracking of oil. Cracking allows us to take long carbon chains and produce smaller carbon chains from them. Hydrogen cracking is done in the presence of hydrogen gas and forms only alkane products. One of the most important aspects of this chapter is the ability to now functionalize a previously unfunctionalized carbon chain. We're able to take an alkane and add a halogen to this alkane through chlorination and bromination. These alkanes can then be used in a slew of different substitution and elimination reactions to form a variety of products through synthesis. Otherwise, an unreactive alkane can be functionalized and used to convert into a variety of different functional groups. There are only a few reactions covered in this chapter, but we can see the synthetic utility and importance of these reactions.